Okay, welcome everyone. So today it's my pleasure to welcome Mengjia Xu, and she'll be talking about adaptive time stepping for learning temporal graph embeddings using transformers. Yeah, thank you.
Can I use my presenter view?
Yeah,
Hello?
we see you. Yeah.
Okay. So thank you so much. So thank you for the invitation. Today I'm going to present our recent work. Actually, it's on the archive now, but under review. Is about adaptive time stepping for learning temporal graph embeddings using transformers. So this is a joint work with PhD student at Brown University Applied Mathematics. Okay, let me choose back. Now it's good. So
yeah, we could see you. Yeah.
Okay. Because I'm using another monitor. So today my talk is about adaptive time stepping for learning temporal graph embeddings using transformers. My name is Mengjia Xu. I'm an assistant professor from Department of Data Science at NJIT. So this work is a joint work with a PhD student, Alan, from Brown University Applied Mathematics, and postdoc, Dr. Bora, and Professor George Kaniadakis at Brown University. So today my talk will cover four main parts. First, introduction. Second, a quick review of our prior paper on the dynamic graph embedding using graph-to-Gauss method. Based on this paper, we propose another improved work on the adaptive time stepping for learning temporal graph embedding using transformers. And lastly, I will give a summary. So first, there are a lot of real-world data from different domains can usually be modeled as networks or graphs. So there is a paper from the 2023, as shown here, mentions that everything actually in the real world is connected. So for example, the human brain networks and the financial networks and the protein networks, and also there are a lot of social networks, very large scale, and also the transportation networks. And recently, graph embedding approach has become the very promising for learning informative graph representations in the Latin space. And it enables learning powerful and highly informative representations by incorporating very important geometric information. For example, the graph topological property or additional node features for downstream tasks. And recently, I think everybody knows that there are two important works proposed by DeepMind on the protein folding network AlphaFold, and also another work on the mass proof and the discovery. They are both highlighted on the Nature and the Science paper in 2021 and recently. So it's very important work. So today I'm going to mainly focus on two types of graph embedding methods. So first one is a deterministic graph embedding. This is a more studies belongs to this type because they can map sparse high-dimensional non-Euclidean space graphs into a low-dimensional space as a continuous dense vectors. Basically, each graph node in the original space can be encoded as a lower dimensional continuous dense vector. However, for example, the very famous paper, Node-to-Vec paper proposed by the Stanford group and Deepwalk and Line and many other approach. And the other type of graph embedding method called the stochastic graph embedding. Basically, they can map high-dimensional sparse non-Euclidean space graphs into a dense functional space. So each graph node in the original space can be encoded as a multivariate Gaussian distribution. So in terms of the mean and the variance vector, so it can provide an important uncertainty quantification property. And more different approaches I have summarized in my previous SAM review paper in 2021, published in SAM review. So the stochastic graph embedding method, there are several studies already. I think the first one I raised the paper is from a Germany group. Is this paper actually. So we have, based on this approach, developed two different methods on temporal graph. So this first paper is proposed for pure and single large scale static graph. And here, this slide, I want to mainly present what are the advantages of embedding uncertainty in the latent space using the stochastic graph embedding approach. So if you look at these figures, we can see this is the first figure A. We show the neighborhood diversity on the x-axis, and y-axis show the averages sigma, basically the embedding space, each node level. Actually, this is the average over all graph nodes. The sigma mean is the standard deviation for each graph node. We can see the node diversity for in the graph increase and is like linearly increase with respect to the average sigma. So the uncertainty in the latent space can help us to capture the neighborhood diversity for the graph nodes. So that's a very important property. And for the figure B, we can see for its average sigma corresponding to the training epochs, and the latent embedding space, the embedding size is 64. So the sigma vector has a size of 64. So we can see during the training, we can see after almost 550 epochs, there are several dimensions keep stable. So they still have the very small sigma, but the other 58 dimensions will continuously grow the average sigma. So it means, so the right curves, these are the latent dimensionality of the graph. Actually, I think it's corresponding to 6 or 4. Yeah, 6. So this is 6 dimensions actually corresponding to the latent dimensionality of the graph actually captures how many number of the communities in the graph. For example, the social network, like the LinkedIn or Twitter, and how many communities in the huge, larger scale graph. And the last figure, they did another experiment to verify this result. So we have 64 embedding size, and we keep to dropping some dimensions in the latent space. We can see in the very beginning, until you drop the last 6 very important dimensions, and then the average accuracy score will drop down. If you drop down the 58 dimensions, which has very high sigma values, means high uncertainty, and then it doesn't affect the AUC and the average precision score at all. So, but if you remove those very latent dimensionality, the important dimensions, and then actually the performance will drop down. So that shows how uncertainty quantification is important for the embedding. And here, this slide, I want to show the stochastic graph embedding for both static and temporal graphs. So this is a same basically summarize the paper from the TUM in Germany. So each graph in the stochastic graph embedding each graph in the high-dimensional space, we can represent as a GC matrix, and they can embed into a lower-dimensional distribution space. So each graph node is encoded as a lower-dimensional Gaussian distribution. In terms of the mean vector and covariance matrix, the covariance matrix is a diagonal covariance matrix. Actually, on the diagonal elements are all the sigma values, as I shown in the previous slide, the sigma values. So the mean vector will indicate the positions of nodes in the embedding space, and the covariance matrix will determine the uncertainty of the nodes or relations in the graph, in the knowledge graph. So in the latent space, we can see the important advantage of this stochastic graph embedding method is uncertainty quantification. So for each graph node, the dot here shows the mean vector. And however, the uncertainty, basically the standard deviation can show the uncertainty. Basically, as I shown in the previous slide, they can show the neighborhood diversity of this node, and also they can help to capture the latent dimensionality of this large scale graph. And all of these latent embeddings, we can use the mean vectors for many different downstream tasks. For example, we can do link prediction or node classification or community detection and many different graph inference tasks. And based on this stochastic graph embedding, the important advantages, we have conducted two different works for static functional brain network using this method for two different tasks. First one is applications. First one is Alzheimer's disease early stage prediction, and another is evaluation of cognitive training effects with human neuroimaging data. Basically, we focus on the functional MRI data and MEG data set. So they are the two different neuroimaging modality to measure the brain activity in our human brain for the Alzheimer's disease or patients. So these are the first two papers corresponding to these two works. And last two papers corresponding to the right side, we also have studied some stochastic graph embedding method for temporal graphs, because there are many real-world data sets. Actually, the graph is changing. The graph is changing over time. For example, here, this is a temp. So it's very important to capture the temporal dynamics over time. This figure show this, if you look at it here, this shows the different time steps, different graph snapshots over time. And we can see there will be some new added nodes, the red as shown in red here, the V8 and V9, and also here the V10 and V11. They are the newly added nodes. And sometimes they will also have some new edges and also remote edges and so on. So the first work we actually published in 2022 on the which journal, the TNLS attribute section on the dynamic stochastic graph embedding method. So we call this model called Mengjia Xu. But based on this work, we recently developed another approach on transformer-based temporal graph embedding, because we want to model long-term temporal evolution history information. And in this work, Mengjia model, we actually is very limited in that aspect. And we also want to capture dynamics with different time intervals, and also for any graph embedding approach, the scalability is also very important. So that's basically what we have done for graph embedding approach for both static graph and temporal graphs. And today in the following, I will focus on the recent work, transformer-based temporal graph embedding, but I will also give a brief overview of this G2G approach. So next, I will give the briefly review of our prior dynamic graph Gaussian embedding method. Okay, so so this is basically main framework or workflow of this approach. This is for static. First, I want to, before introduce the dynamic graph embedding, I want to first introduce in detail about the static graph embedding, how to embed each graph node into a Gaussian distribution, multivariant Gaussian distribution. So here, started from input graph. This is for example, this is a graph represented with the node set V and edge set E with adjacent matrix A. Basically, is a square matrix. The number of nodes times the number of nodes, and also the attribute matrix we have X here is a 2D dimensions 2D matrix of size, the total number of nodes by the number the feature dimension, the feature size. And it's a very simple actually model architecture. That's why this approach is very when you train the network is very efficient and get very good result. And also it can provide the uncertainty quantification. That's why I focus on this method for for a few works. So here after this input graph, we will input the graph HS matrix and also the attribute matrix A and X into a basically an encoder. Basically, it's a MLP, multi-layer perceptron, dense layers. So we first learn the hidden representation for each graph node in the original graph as a intermediate hidden representation. So basically H here. This is a typical dense layer using the ReLU nonlinear activation function, and W is the weight, the parameters, and B is the bias. And after we learn the intermediate hidden representation, we use another two projection heads. The first one, linear mapping, we basically to output the mean vector in the Latin space for each graph node. And the nonlinear mapping, we use the ReLU nonlinear activation function because we want to make it larger than 1. Sorry, not larger than 1, larger than 0. So, and here, this is also actually only single layer. And then we will output the mean vector and also the covariance matrix. Basically, the covariance, we first learn the sigma vectors, the standard deviation vector. And then this is similar like the variational autoencoder, but we don't have the decoder part. So now we can output each graph node. So I is the node index here. For each graph node Vi here, we can learn a multivariant normal distribution for each graph node. And then another important step, because we don't have decoder part, and how can we optimize the whole network? So there is another important step in this method is we need to generate some node triplet set here based on the original graph, basically based on the adjacent matrix A here, this matrix. And we need to, based on key hop neighboring method, to sample each graph node, several hops neighbors, like 1 hop neighbors of node I, and also 2 hop neighbors of node I, and so on. And then basically we can set up the key hop, the key value. We usually choose, because of considering the computational cost, we usually choose k equals to 2. And we will build some node triplet set for all graph nodes in the original graph. basically the reference node we can also sometimes we call anchor node, and the nearest node, and also the furry node. The furry node is actually basically like two hops, is not connected with the reference node. I want to. Yeah, this may be better. Use this. This node is far from the reference node compared to the nearest node, because the nearest node with the reference node, they are connected together directly. And this is how we generate a node triplet from the original graph. And how can we use this node triplet? We basically, now we go to the loss function. This is a purely unsupervised learning process, but maybe you can also think about this semi-supervised, because we manually actually engineer this part. We choose the node triplet from the graph node, and here the loss function we basically is based on a square exponential loss, and we use the Kerr divergence to mirror the dissimilarity between the multivariate normal distribution for each graph node pairs. So here we, based on the node triplet, reference node and nearest node and far node set, we can compute, basically we want to minimize the Kerr divergence, the dissimilarity between the positive node pair, which are the reference node and the nearest node. And then we want to maximize the dissimilarity between the reference node and the farthest node using the Kerr divergence. And Ni here, we represent the multivariate normal distribution for each graph node in the Latin space. So this is basically a triplet-based contrastive loss, and we use the Adam optimizer to optimize the whole model. So is there any question about this workflow? Okay, so now this is how to learn static graph, and now we want to learn a temporal graph. So we basically, based on this static graph embedding, we extended to a temporal graph. So this is our paper in 2022, and our GitHub code link is shown here. And this is basically the algorithms we developed based on the static graph embedding approach. And here, how can we learn temporal graph embedding? Basically, this is a very simple extension. So we focus on discrete time temporal graphs over time steps. It's not a continuous time temporal graph. So here we have several graph snapshots, G1, G2 until G capital T here. And so each graph snapshot, we started from the first step, time step. We learned the stochastic graph embedding for G1 here, and using the similar model architecture. And here the important, this is we learned, we use also the same contrastive loss function. And one important step is how, because when you go to another time step, there will be different number of nodes, and so the graph adjacent matrix will change. So we need to use net wider is actually a method developed in I forgot which year, but it's from Google. So we can change the model, basically the encoder part, the model architecture, the hidden sides, based on the number of the nodes, based on the number of the increasing nodes. V1 is a total number of nodes in time step 1, and V2 is a number of nodes in the time step 2. So we can, based on this graph node numbers, we can adaptively modify the encoder architecture, basically the input size and hidden layer size. And then to learn the second step graph embeddings, we use a transfer learning approach. we, based on the hyperparameter CT1, learned from the first graph snapshot, and we started from use the pre-trained parameter and to train the second graph snapshot to learn the graph embedding in the second snapshot. And continuously we will learn a temporal based triplet based contrastive loss here. This is a kind of similar like the recurrent neural network, but it's more efficient compared to that one. And here, this slide we show we have verified experiment. We conducted experiment on 8 different benchmarks, temporal graphing benchmarks. And this is 2 different benchmarks visualization over time steps. This is the 41, 44, 48, and 50 time steps for the SPM dataset, which is a synthetic dataset. And the second dataset is a DIG dataset. So they have a total number of 30,000 around number of nodes and edges, like 87,000 number of edges, and 90 time steps in total. And SPM is relatively small graphs, so they only contain 1,000 nodes and but a lot of edges and 50 time steps. This is show the growth rate of edges over time steps. We can see SPM dataset change very smoothly over time. And here the DIG dataset change very dramatically, has a highly transitional dynamics. And so this is all the 8 benchmarks descriptions used in our experiment and the training time steps, validation time steps, and test time steps. Basically 70% we use for training and 10% for validation and 20% for test. So we have tested the method on different different large scale graphs. And here we evaluate our method on temporal link prediction tasks with the proposed method dynamic graph embedding for these 2 different benchmarks, SPM and DIG. And we tested based on different embedding sizes, 16, 32, and 256. And we can see that this is a metric we use mean average precision. And the different x-axis show the embedding, different embedding size. We can see for the large scale data sets, we can use only L equals to 64 embedding size to get the highest mean average precision accuracy for temporal link prediction. And this slide we show beyond of this temporal link prediction task, we also show the uncertainty quantification results over time for temporal graph embeddings and different embedding sizes. So these are the 8 different benchmarks. And the uncertainty basically is the average sigma over time steps. We can see the uncertainty can be measured as a function of time step t over time, and also different embedding size. We can find a very interesting correlation between the optimal embedding size and the effective dimensionality of the uncertainty for 8 different benchmarks. And these results help us suggest a clear path how to select the graph optimum embedding dimension by choosing L larger or equals to the optimal uncertainty dimensionality du here. So this is the optimal embedding size LO for the first benchmark AS, and also other 7 additional benchmarks, SBM, UCI, and Bitcoin dataset. So we can see the UQ uncertainty quantification dimensionality DU here is 64. So this 64, these numbers are obtained based on this plot. So for example, we can find for example, the SBM here, this SBM is 64. So we can see 64 is a green curve. We can see the uncertainty actually 64 has a very small uncertainty. So it is, and actually there are other like 128 and 256 are all very close to each other, but we will choose the smallest one because we don't want to use larger embedding size. That will be increase the higher computational cost. And this optimal embedding size, basically we obtained based on this temporal link prediction results. In our paper, we have all the box plots like this. And basically, for example, the dig, here we find 64. 64 achieved the highest temporal link prediction results. And this equal dimensionality we obtained from this figure based on the uncertainty quantification results. So this is our main findings of this paper. So we want to find the optimal embedding size and also guided by the uncertainty quantification on dimensionality. So this I think, this paper is basically applied on some public benchmarks, but if we want to extend it to some real applications, may be more interesting in the future. And so based on this proposed approach, we have some limitations for this paper because we only use the previous time step. That's a big limitation because we can only capture the short-term dependency in the temporal graph. But if we check the constant similarity with the preceding 10 time steps, for 3 different benchmarks, we can see this is a constant similarity. Basically, we compute the constant similarity between the adjacent metrics at each time step and with the previous 10 time steps. And we can see actually there is a similarity with graphs from previous time steps and changing over time. So if we can leverage this similarity to improve the link prediction performance by capturing long-term temporal dependency across multiple time steps in the past. So that's our main motivation to develop another improved approach using transformers. And we also actually, in the very beginning, we just want to do a simple experiment using, multi-step method. We want to, this is a typical multi-step method to initialize the weights, because in the previous paper, we only initialize we only take advantage of the previous time step W, the weights, pre-trained parameter W, t-1. And here we want to, for t+1, we want to take advantage of the previous 2 time step T and t-1. So use the coefficients theta here. And this is a result. We find actually the multi-step method get better results but not get better results for the stable benchmark, the SVM. In the previous slide, I showed this benchmark actually show very smooth transition. So multi-step method may not have a lot on this benchmark actually, but for other like this reality mining and the UCI benchmarks, they show very highly dynamic dynamics over time. But these 2 benchmarks, the multi-step method actually show better results. But this UCI, why it doesn't show better results? Because it's very highly highly dynamic. This benchmark is very difficult benchmark here, this one. So based on this motivation, we want to, and also since the very powerful transformers in capturing long-term dependency, so we developed the adaptive time stepping for learning temporal graphing using transformers. And this transformer model, I think I wrote here, is developed in 2017 based on encoder and decoders model architecture, and use a very important mechanism, self-attention mechanism, and the positional encoding, and stack of different encoders and decoders to learn the very accurate embeddings for, and also they can predict do sequential learning very well. And important property is they can learn the dynamics in language models, and also recently like computer vision tasks like vision transformers without catastrophic forgetting. So basically they can capture more long-term dependencies. And this is a self-attention mechanism. They can learn the token with the neighboring tokens with different coefficients weights. And here is we propose the TransformerG2G approach to learn the temporal dynamics for graph representations. And how actually there are several other papers using transformers for learning temporal graph embeddings, but I think we use in different ways. Recently, we are revising. Actually, 1 month ago, we were revising the paper based on the reviewers' comments. So they also mentioned that there are several other transformer papers, but we read those papers. They actually use very different way from our paper. Our paper is basically we learned the temporal node embeddings. So how we do that? In the graph, we have VI. So for each graph node VI, we have a temporal, the node attributes. So we basically, this is we also focus on discrete time dynamic graph G here. And so we basically input the encoder of the transformer encoder. We only use the encoder part in our work. So we input the VIT with the previous L time steps. So L is a hyperparameter in our work. We can predefine this parameter from 1 or 5. Basically, 1 is use the previous 1 time steps. And then here, we basically input this node level attribute vectors. So each node attribute vector can be think about as a token. So we can input to the encoder of the transformer encoder, and to learn here, this is a 2 additional projection head. This is basically combined with our previous work. We still want to capture the uncertain quantification in our embedding space. So we combine with our previous work to learn a multivariant Gaussian distribution for each graph node in terms of the mean vector and the covariance matrix. And here, this is actually the diagonal elements of the covariance matrix. And this is basically the very simple improvement. And in the proposed TransformerG2G model, we have the node embedding learned by a transformer encoder with self-attention. So in this paper, in this work, we basically want to use the self-attention mechanism to capture the dependency with the previous multiple time steps. So, and the output multivariant Gaussian distribution for each graph node, not a single vector, is a density function. So here, this is a Gaussian distribution for graph node I. And then we minimize the same loss function using triplet-based contrastive loss. Here, this is the same as the previous work we use. And this is our paper on the archive version. If you're interested in, you can download that paper. And in this work, we also apply a very interesting plot called temporal edge appearance called temporal edge appearance plot. Basically, they can help us quantify the temporal dynamics better than the growth rate of edges in my previous slides. So this metric is very important and very useful. So it's proposed in this paper, actually in 2022. And so this we call T-plot. So it can define the property of so they have a very important metric they call novelty. So it defines a portion of repeated edges versus newly observed edges from each time step in a dynamic graph. So here, so the red bars show the new edges and the blue bars show the repeated edges. So we can see an over time step T. We can see more interactions happened in this benchmark. This is for UCI benchmark. And the novelty value is 0.75. So it's relatively high dynamic. And we can also see which time steps they show like more interactions happened here actually around 10 to 20 or 25 time steps. And around here is almost is something happen. So because of this T-plot and also the novelty metric, we can easily capture the temporal dynamics within the dynamic graph. And another important point is when the novelty is very high, and the memorization approach would not help much with improving temporal node representation learning. Remember, when we do the simple multi-step approach for this benchmark UCI, we didn't get improved performance for link prediction using multi-step because the novelty is very high actually for this benchmark in some time steps. So if you want to use the memorization approach, like capture long-term dependency, sometimes this could not help actually. So this is the comparison results for using transformer and also compare with our previous approach, the IG2G paper, in terms of the temporal link prediction tasks. And we use two different metrics, mean average precision and MRI. These are the typical two metrics used for temporal graph embedding studies. And look back here, this is we basically we look back at different time steps in the previous time steps in the history information, how much historical information we used in the model. So for SBM, we can see this is more clear. The first blue bar show our previous that IG2G paper results, and the yellow bar show the new transformer model-based performance. We can see for the highly smooth transient benchmark SBM dataset, we didn't get improved results, even use the self-attention and transformer, because the previous single time step that's enough for our dynamics learning. And however, for reality mining dataset, we can see this is a T-plot. This is a T-plot, and the novelty is 0.0761. And this plot shows the cosine similarity with the previous time steps, 10 time steps. And we see the MAP increase with the look back to 4. This is a look back step for the previous time step 4. We can see the improve. This gets the highest performance for MAP for temporal link predictions. And the uncertainty also decreased until look back 4. So this is a very important result using the transformers. We can see is improved a lot compared to our previous paper, the blue bar. And the similar Bitcoin dataset is we also achieve a highest MAP value when lookback equals to 4. And this benchmark, they have a lot of time steps, 137. So this slide, I show another important findings for the self-attention. We visualize the attention metrics for the reality mining and benchmarks. So this is a time-dependent attention matrices for graph node 6 and using lookback 4. So we can see actually the attention matrix is a 5x5 matrix. And we can see actually the yellow one show high weights. And the red side, we show the node degree. Also temporal dependent node degree plot for node 6 at each time step from 5 and 6 and 7 and 263 for rating mining benchmark. We can see for example, this plot, the t equals to 10, the time step 10. And here we can see this is the highest node degree. And also here, the attention weights also show very high for these time steps. So this is a very interesting correlations between the attention weights and also the node degrees. So basically, I think the self-attention help us to learn the time steps with a higher node degree. So that time step may be more important for and more rich information can help us to learn more highly informative node representations. So this is and this shows all the overall experimental result for the temporal link prediction based on the proposed TransformerG2G in terms of the MIP and MRI metrics using different lookbacks for 6 benchmarks. I think we also have some new experimental results in our revised paper. If you want to, you can see more updated experimental results from the archive paper. Yeah, we can see that using Transformer G2G approach, we get some improved results. But the SBM, we didn't get better one. It's a highly smooth method. And here, summary. So Transformer achieved better performance compared to our proposed method for most of the benchmarks because it enables effective learning of temporal graph embedding from long-term memory. So we have the hyperparameter L look back time steps in the past by using self-attention. And the T-plot provides a good metrics that can help better characterizing the temporal evolution pattern in dynamic graph. And by computing the portion of repeated edges versus the new edges. And importantly, by examining the attention weights, we can uncover temporal dependencies, identify influential elements, and gain insights into the complex interactions within the graph structure. For example, we identify a strong correlation between the attention weights and the node degree at the various stages of graph topological evolution. And thank you so much. Thank you for the invitation. I'm very glad to present my work here. Thank you.
Thank you very much. Thank you. Any questions or comments?
I have a question.
Yeah.
Sure.
So is it possible, for example, to fix the number of nodes during the evolution of the graph? Let's say maybe you want to learn a feature on the nodes that is evolving, but the number of nodes themselves are not changing.
You mean the number of nodes changing over time?
They are not changing, they're fixed, but the features on the nodes are changing. Let's say maybe you have a fixed number of people in that graph, and you want to learn some interaction between them, but the number of people there in that graph is not changing in some way.
Sorry, the internet is a little unstable here. If I understand well, so you basically means the level feature changes over time, right?
Yes, but the number of nodes or the number of nodes themselves is fixed.
Oh, Oh, that's interesting. Oh, yeah, but yes, that's interesting. But I think in all of our 8 benchmarks, they are all public data set.
Okay.
I don't think we have fixed number of nodes, only in the SBM, but SBM, we don't have features, actually. That's a synthetic data set. Many papers using this synthetic data set because they want to show this highly smooth one. But that's very interesting. Maybe some real application have this case.
Yeah, I mean, the kind of applications I'm interested in with graphs is the
Yeah,
nodes on the graphs, the features on the nodes of the graph changes with time, and you
yes.
might have like edges between them that is also fixed. The edge features might be fixed, but the features themselves um evolve with time, and the number of nodes also is fixed in some way.
Yes, that would be very interesting. But I think in the approach, in the method, we consider the attribute, not the attribute in the model architecture.
Mm-hmm. Okay.
I think they can yeah, but we didn't, yeah, we don't have experiments on such benchmark. But I think the model can capture the dynamics, but
Okay.
I'm not
Okay.
sure the performance because
Uh,
we didn't, yeah, we don't have this benchmark. Yeah.
right. Okay. Okay. Thank you.
Thank you so much.
I have a question also.
Sure.
Yeah. So in the model you made, you assume that the graph is homogeneous or is heterogeneous?
Oh, so all the benchmarks we didn't consider like knowledge graph. The graph has different the node has different types. We basically is kind of homogeneous. Yeah.
All right. Other questions or comments? Yeah, okay, thank you. Actually, I have like general questions about GNNs. So you know that there's some people, like, for example, they covered branch quota or using like neural networks by having different connections. And I was wondering here if you can like recover like finite element methods, for example, using neural networks where you can, yeah.
Yeah, the grand paper, right? Grand or graph.
Graph paper, okay.
Yeah. Graph is more, I think is improved compared to grand. Yeah.
Oh,
Yeah.
okay.
Yeah. Actually, I think in the group at Brown, actually we also had some work study on that side. Yeah.
Oh, okay. Yeah, so maybe you can send me the references because I'm still new to GNN, so I'm just having questions in my mind. So maybe you can.
Yeah. I think we study fractional order. Yeah.
Okay. Okay.
Yeah, I think they also, yeah, we discussed this, but in this talk we didn't mention that, but yeah, some work on related with that.
Okay. Yeah. So yeah. Okay. If you can send me some references by email. Yeah.
Yeah. Okay. Thank you so
Right.
much.
Okay. Yes. Are there other questions or comments? Okay. So it seems not. So okay. Thanks again, Mengjia, and then I'll talk to you soon. Yeah.
Yeah. Thank you so much. Bye. Have a
Bye.
good
Bye.
day.
Thank you. You too. Thanks. Bye.